So now we will go for variation method for the excited states. As I said, and variation method is very useful for the ground state. Okay, especially for the hydrogenic system in which the system contains single electron. It's useful. Even it is a complex system, and we can convert those system into hydrogen-like system, and we can use it. Suppose if you are going for the excited states, the errors will be more. And for the first order excited state, it's okay. Okay, we will see. And very important thing is, we have the wave function for the ground state, and we have the another wave function for the excited state. These two wave functions should be linearly independent, and those two wave functions should be always orthogonal to each other. Very important concept in variation method. These two conditions should be satisfied. We have a wave function for the ground state, we have the wave function for the excited state. These two wave functions should be linearly independent, and they should be orthogonal to each other. Only then those conditions should be satisfied. Okay, very important one. So as I said, the wave functions are orthogonal to the exact ground state eigenfunction. Okay, so psi a stands for the ground state wave function, phi n plus 1 stands for the first excited state wave function. These two wave functions should be orthogonal to each other. This is equal to 0. Okay, these conditions should be satisfied, and these two wave functions are linearly independent vectors. One vector cannot be written in terms of another vector. So this is a tail wave function. Okay, this is a tail wave function. This is also a wave function for the ground state. So of course it must be normalized and orthogonal wave functions. So it implies that the first one, this is psi 1 with phi n plus 1 equal to 0, psi 2 with phi n plus 1 equal to 0, psi n with phi n plus 1 equal to 0, of course. So we know already this. This is your initial and this will be your final. Okay, one. Second one is, this is inner product, scalar product. Okay, this is inner product or a scalar product, which is equal to 0, orthogonal condition. So these two conditions, linearly independent, and second one will be orthogonal to each other. So these two conditions should be satisfied for the first excited state, for any other excited states. So now we are going to prove this one. So phi can be expanded in terms of psi j with the expansion coefficient aj. Okay, so using expansion theorem, so we know already. So phi just expand. So aj psi j, so which is nothing but a1 psi 1 plus a2 psi 2 goes on. And corresponding, this is your ket vector in terms of ket vector. So corresponding bra vector can be written as like this. So corresponding bra vectors, correct? So you have aj here, so ai star. So this must be written in terms of bra psi. So which is nothing but a1 star psi 1, a2 star bra psi 2 goes on. So we know the expectation value of the Hamiltonian is given by this expression 4.110. We know already. Now just use 4.108 and 4.109. So these two equations here in this expression. We will take first numerator first. So just taking the numerator. So phi, this your phi is here. So ket phi, I can use this expression. Bra phi, I can use this expression. Correct? So which is nothing but your ai star aj H sandwiched between your psi j and psi I. Is it okay? Fine. Now, similarly for the expression where the first excited state. Now summation, look at the summation. It goes, I goes, summation over I, summation over j. Here for the excited state, summation over n plus 1, summation over j. Okay? Is it okay? Any doubt? So summation over n plus 1, first excited state. Here summation over j. The same condition for the first excited state. Now we know that H operates on psi j will give you Ej psi j. So Ej psi j. So that can be written as like this. Ai star Aj will give you, if I equals j, that will give you mod Ai squared. So multiplied by Ai. Summation again goes from I equals n plus 1. So this can be expanded in terms of your I will be n plus 1, so this must be a n plus 1 squared, a n plus 2 squared, and e n plus 1, e n plus 2 goes on. Is it okay? So this is for the numerator. Okay, this value will be always greater, this value will be greater, so this must be greater than or equal to e n plus 1. So we know already the variational theorem. Using variation theorem we know already this. Now just use equation 4.108. so this is your equation 4.108. so expansion theorem, phi can be written as exactly like this. Now that can be written as phi, which is equal to phi 1 plus phi 2 plus phi 3. Use expansion theorem exactly like this. You compare this and this, that will give you phi 1 which is equal to a1 psi 1. Similarly phi 2 which is equal to a2 psi 2 goes on. So psi 1 stands for, as I said earlier, this is for the ground state wave function. This is the initial one. This is a result that we are going to get, is the result. So this will be your excited state wave function. Both should be orthogonal to each other and linearly independent, these two conditions. Okay, and so both should be orthogonal to each other. Suppose they are not orthogonal, we will have to make these wave functions orthogonal to each other using which you have studied already in mathematical physics, Gram-Schmidt process. Okay, if they are not orthogonal, we will have to use Gram-Schmidt process to have orthogonal properties. If they are not orthogonal, if they are orthogonal, well and good. Okay, so both should be orthogonal to each other. So ground state wave function and your excited wave function should be orthogonal to each other. If they are not orthogonal, we will have to use Gram-Schmidt process. Okay, now I am going to multiply on both sides by bra psi 1. Okay, bra psi 1. I am going to multiply on both sides by bra psi 1. So phi 1 psi 1 which is equal to a1 psi 1 psi 1 psi 1 psi 1 which is nothing but 1. So you will get a1, but they are orthogonal to each other. You have psi 1 and phi 1. So a1 equal to 0 or psi 1 with phi 1 will be equal to 0. So now these two which is equal to 0 in the sense that these two wave functions are orthogonal to each other. Now we are going to have the situation if they are not orthogonal. We are going to have the situation if they are not orthogonal to each other. We are going to this wave function phi 1 which is not orthogonal to psi 1. Suppose if you are orthogonal, well and good, it's okay. Suppose if you are not orthogonal, we will have to use Gram-Schmidt orthogonalization procedure to go for orthogonal vectors. Already we studied in mathematical physics. So now phi 1 is here psi 1 is here, correct? Both the wave vectors, they are not orthogonal, they are not perpendicular to each other. Okay, they are linearly independent vectors. Now we are going to use Gram-Schmidt process to have these two wave functions are orthogonal. We are going to try. So now phi 1 is projected here like exactly like this. I am going to measure phi 1. I am going to measure phi 1. That means phi 1 falls on psi 1. It's a projection vector. Okay, so projecting on the surface. So phi 1 falls on psi 1. A part of phi 1 falls on psi 1. A part or a component of phi 1 will fall on psi 1. That part is nothing but this one, scalar product, psi 1 phi 1. So I am going to project this one here. The part will be here psi 1 phi 1. Okay, now this phi 1 can be written in terms of phi 1 parallel and phi 1 perpendicular, correct? So this is a vector. This vector can be written in terms of components. So this component and this component, correct? So phi 1 can be written as a parallel component and perpendicular component. And I am going to equate these two. This is a vector quantity, this is a scalar quantity. After multiply this, only then this can be equal to this. Is it okay? This logic is okay? So as I said, phi 1 can be written as parallel component plus perpendicular component. Okay, perpendicular component. So I am going to take phi 1 perpendicular this side. So phi 1 minus phi 1 parallel. Phi 1, let it be like this. Phi 1 parallel is a vector quantity. This is a scalar quantity. If I multiply this with this, only then this will become a vector quantity. So I will have to multiply with psi 1. This quantity multiplied with psi 1 along the surface. So it's a projection vector. Okay, it's a projection vector which we are going to see now. So phi 1, let it be like this, and psi 1 phi 1 with psi 1. Okay, and and this is your phi 1 psi 1. Okay, psi 1 phi 1 with psi 1. Okay, so this is your number. It's a scalar quantity. Psi 1 with phi 1 is a number. So I can take this psi 1 anywhere. So I'm going to bring this psi 1 this side. Is it okay? Come on, I repeat. This is your scalar quantity, number. It's like phi x. I can write x phi also. Doesn't matter. So I can take this one to this side. So this becomes psi 1. This will be phi 1 psi 1. This is nothing but your completeness. Outer product, which is nothing but projection vector. Okay, so we are going to have two wave functions which are not orthogonal to each other. We are going to use Gram-Schmidt process applying projection vector. So this side will come to here, will come this side. So phi 1 perpendicular, this is phi 1 perpendicular. Now I am going to make another parallel to this vector. This vector will be exactly equal to this vector. I am going to call this as phi 2 vector. So instead of phi 1 perpendicular, I can write this as phi 2. So phi 2 is given by this. And of course, the unit vector for phi 2 is given by this one. And unit vector for phi 1 it can be written as exactly like this. The unit vectors for psi 1 can be written as like this. A by modulus A vector, which you have already said for unit vector. A vector divided by modulus of A vector is a unit vector. So I can write unit vectors exactly like this. Now look at this phi 2. Phi 2 vector is here. Okay, phi 2 vector. So phi 2 vector is perpendicular to psi 1. That is the idea. Earlier phi 1 vector is not perpendicular to psi 1. We have obtained now phi 2. Okay, this phi 2 vector which is perpendicular to psi 1. This is orthogonal. Both are orthogonal to each other using Gram-Schmidt process. So this phi 2 is vector is perpendicular to psi 1. So both are perpendicular to each other. Now we are going to prove whether really it is perpendicular or not. We are going to prove. Let us see. I am going to take the inner product with psi 1 with phi 2. So as I said just now I said psi 1 is perpendicular to phi 2. Whether it is true or not, let us see. I'm going to take the inner product with psi 1. So psi 1 phi 2 which is equal to psi 1 phi 1 minus psi 1 phi 1 phi 1 psi 1. So we know already this. Correct? Now psi 1 answer will be 1. So your psi 1 phi 1 minus psi 1 phi 1 will be 0. If it is 0, both the vectors must be orthogonal to each other. So it's very clear that phi 2 is perpendicular to psi 1. So both the vectors are orthogonal to each other. Is it okay? Simple one. Similarly, we can go for another vector, which the vector is like this. Okay, we have taken a single vector. Okay, now we can have another vector. Again, we are going to measure this vector. This vector will project on phi 1 and psi 1. We can also take number of vectors. Okay, this will project on phi 1 first, then after that it will project on psi 1. So we can have the third vector. Okay, and we can have a similar equation. First it will project on phi 1, then after it will project on psi 1. First it will project on phi 1, after that it will project on psi 1. So it is like that. Now I will have to prove that phi 3, which I have chosen this vector, this must be perpendicular to psi 1. For that I will have to go with taking the dot product of psi 1, taking bra vector of psi 1 on both sides. So psi 1 phi 3, psi 1 phi 1. So we have psi 1 phi 1, psi 1. This is the number. So it's a number. So that's why psi 1 phi 1 is here. Psi 2 phi 1, again it's a number I have pulled out. So this one will be psi 1 phi 2. What are psi 1 psi 2? This is equal to 0. If it is equal to 0, this term will not appear. Correct? What is the answer? This will be 1. So this minus this 0. So if it is 0, psi2 phi 3 equal to 0, it implies that psi2 and phi 3 are orthogonal to each other. So in that way we can have number of excited orthogonal wave vectors. So those vectors should be linearly independent vectors, first condition, and another condition will be those should be orthogonal to each other. Okay, they must be orthogonal to each other. Clear? So we can construct the orthogonal set. If they are not orthogonal to each other, we will have to use Gram-Schmidt process using projection vector to have orthogonal sets. Okay, the energy corresponding to the state phi 2 is taken as E2, and similarly the energy corresponding phi 3 is taken as E3, and your two systems should be always greater than that of the Hamiltonian, as usual, using variational theorem. So the generalization. So we have done for 2 vectors, we have done for the 3 vectors, this is for the n vectors, this is generalization. So this can be given by equation 4.125. So phi n plus 1 equals phi 1 minus summation over I equals 1 to n and this factor, this term. So this is a scalar quantity with psi I. Any doubt? And psi A stands for the ground state, your phi n plus 1 stands for the excited states. So they are orthogonal to each other. The answer that we are going to get using variation principle will be always greater than or equal to the 2 energy system. So that is for the excited state. Any doubt? Okay. So now we will go for the summary, whatever we have studied. Okay. The basic principle of variation method is to guess the trail wave function according to the physical properties that we have already studied earlier for the problem, which consists of some variation parameters. Okay, adjustable parameters. So variation parameters inverse of Bohr radius. Okay, inverse of effective Bohr radius. When you study like a quantum dot, quantum well for semiconductor. So what we call this is effective Bohr radius. These variation parameters are fixed to minimize the energy of a trail wave function. The resulting trail wave function and corresponding energy are variation method approximations to exact wave function and energy. The trail wave function that we have chosen should satisfy boundary conditions, some physical properties that it has to accept. So the exact wave function should be normalized. The variation method is a mathematical method that is used to approximately calculate the energy levels of difficult quantum systems. As I said, if it is complicated system, we will have to make into hydrogenic wave system, at least for helium system. It can also be used to approximate the energies of a solvable system and then obtain the accuracy of the method by comparing the known and approximated energies. Known energy is experimental energy. Approximated energies that we have already calculated those energies from our guessed wave functions. The Schrödinger equation can be solved exactly for our model systems, including infinite square well, particle in a box, whether it is finite or infinite, harmonic oscillator, hydrogen atom, and rigid rotator. However, for systems that have more than one electron, the Schrödinger equation cannot be analytically solved. It's a complex system and requires approximation like variation method to be used. The Hamiltonian is known but cannot be solved exactly but tediously with the perturbation theory. So for that purpose only we have used variation method. But it is easy to determine the ground state energy and eigenfunction using variational approach. Here we are going to find the upper bound values. Whatever the chosen values, we will get only those values will be upper bound values. So those values will be always greater than that of your two state energy values. For the eigenvalues and eigenfunctions, we should guess the trail wave function depending on the variation parameter. The expectation value of the energy is expressed as functions of eigenfunction and variation parameter. Therefore, the energy is also a function of variation parameters. The energy is also a function of variation because psi depends on variation parameter. So E also will depend on variation parameter. Then the energy is varied with respect to the variation parameter to obtain the minimum energy because the electron will tend to be in a minimum position. Okay, so that's why we are going to minimize the energy. The value of the variation parameter for which energy is minimum. Using this value of the variation parameter, we find the value of minimum energy from the expression of energy expressed as a function of variation parameter. This value of variation parameter is used to find the eigenfunction for a given straight through the selected guessed trail wave function. So that is the N. Okay. So thank you students. We will start today and we will try to solve 3 problems in the next class. Bye students. Bye.